Good day, class. Today we'll be talking about the following topics on redox stoichiometry. First, I'll be talking about oxidation reduction reactions, or what I call redox reactions. Next, I'll be defining some terms such as oxidizing agents, reducing agents, and we'll teach you how to use standard reduction potential table, or the SRP table. Third, we'll be predicting products of redox reactions through the aid of SRP table. Number four is we'll be balancing redox reactions through the half reaction method. And finally, we'll be performing redox titration calculations. So without further ado, let me discuss what are redox reactions. Redox reactions are all around us. The rusting of iron is a redox reaction. The change in color of an open apple is a redox reaction. And our main power source, which occurs in our cell, which is what we call the electron transport chain and oxidative phosphorylation, is also a redox reaction that occurs in our mitochondria. So all of these are redox reaction. In the rusting of iron, iron is converted to iron oxide. In the browning of apples, phenols are converted to quinones. And in the electron transport chain, NADH is converted to NAD plus, and FADH2 is also converted to FAD plus. So all of these are aided with reaction with oxygen. So in this case, oxygen is converted to water in all these cases. If there is an oxidation reaction, there is always a reduction reaction, and that goes along with it. Fundamentally, redox reactions are reactions that involve transfer of electrons. In oxidation, it involves the loss of electron, which is signified by the mnemonic LEO, or loss of electron oxidation. And in the reduction, it is accompanied by gain of electron, which is used with the mnemonic GER, GER, gain of electron reduction. So when there is oxidation, there is always reduction. When something is lost, something is also gained. Another term that I would like to define is the term oxidizing agent. Oxidizing agent is a chemical substance that causes oxidation of another chemical substance. Therefore, since it is the substance that causes oxidation, the other substance is oxidized, the oxidizing agent is the one that is being reduced. Okay, so in order to remember it, just remember the mnemonic OR. Oxidizing agent undergoes reduction, or oxidizing agent is reduced. Reducing agent, on the other hand, is the opposite of oxidizing agent. Reducing agent is a chemical substance that causes reduction of another chemical substance. Since the other chemical substance is reduced, meaning the reducing agent is the one that is being oxidized. So in order to remember it, you may use the mnemonic RAW, or reducing agent is oxidized. It's just the opposite of OR, OAR. Next, I'll be talking about the standard reduction potential table. In the standard reduction potential table lists all the oxidizing agents and the reducing agents in order of increasing strengths or increasing activity. If we look at the left side of this table, we may see the reducing agents. So in the standard reduction potential table is arranged in such a way that all of the reactions are written in reduction. And therefore, the chemical species that has the largest or the most positive standard reduction potential is one the most positive. The strongest oxidizing agent will most likely undergo reduction, and also the strongest reducing agent will most likely undergo oxidation. Say for example, the standard reduction potential of hydrogen is 0. So everything that has a standard reduction potential, which is signified by EO, that is greater than 0 will most likely be reduced. So tin will most likely be reduced, oxygen will most likely be reduced, hydrogen peroxide will most likely be reduced. Conversely, all chemical substance that has a standard reduction potential that is less than 0 will most likely be oxidized. So we have lead will most likely be oxidized, nickel will most likely be oxidized, and the alkali metals will most likely be oxidized. So the alkali metals are the strongest reducing agents since they are the ones that tend to be easily oxidized. Of all the oxidizing agent, fluorine gas is the strongest, and of all the reducing agents, lithium is the strongest. This is the reason why lithium is used in batteries, because it is the one that can easily transfer its electron to power electronic devices. Okay, let's have an exercise for this. Okay, which of the following is the strongest reducing agent, or the one that is most easily oxidized? So we have copper 2 plus, lead, iron, aluminum. So if you look at this, okay, so the question is which one is the most easily oxidized? Okay, take note that the standard reduction potential table is written in reduction. Therefore, the left side of the equation is the chemical species that undergo reduction, like this one. We have iron, lead, lead 2 plus. And the right side of the equation are the chemical species that undergo oxidation. So reduction is just the opposite of oxidation. So we have lithium, sodium, iron 2 plus, we have copper, and all of these chemical species at the right. So therefore we can identify the chemical species that can undergo oxidation. So these are, we have copper, we have lead, iron, and aluminum. So of all these chemical species, which one can be oxidized most easily? The answer is aluminum, for the reason that aluminum has the most negative standard reduction potential of all these chemical species. So iron has negative 0.45, whereas aluminum has negative 1.66. Okay, if you were asked which of the following is the strongest reducing agent, then the answer is automatically lithium. Which of the following is the strongest oxidizing agent, then the answer is fluorine gas. By the way, what are the characteristics of an oxidation reaction and a reduction reaction? The characteristics of an oxidation reaction are, we have increase of oxidation number and loss of electron. Loss of electron means that the electron is written on the product side. For reduction, we have decrease of oxidation number and gain of electron. When we say gain of electron, the electron is written at the reactant side. Okay, let's have this one for example. F2 plus 2E minus will form 2F minus. Okay, so in this context, we have F2 is converted to from 0 to negative 1. The oxidation state is from 0 to negative 1. So this one is reduction. And the electron is written at the reactant side, meaning the electron is gained from external sources. So this one is a type of reduction reaction. So let's have another example. We have lithium solid will produce lithium ion plus electron. The oxidation state is from 0 to positive 1, and the electron is written at the product side, which means that the electron is lost. So in this case, this one is oxidation. Oxidation is just the opposite of reduction. So if it is written the other way around here, so lithium Li plus E minus will form lithium solid. And since the standard reduction potential is negative 3.04, meaning there is a very low possibility that lithium solid or lithium plus will be reduced to lithium solid, because it should be the other way around. It should be lithium solid will be oxidized to lithium plus ion. Okay, so now we'll be applying this concept to the prediction of products of redox reactions through the standard reduction potential table. Oxidation and reduction reactions occur hand in hand. So when there is an oxidation, there is always a reduction. Therefore, all redox reactions are just reactions of oxidizing agents and reducing agents. Okay, say for example, let's have reaction of aluminum and iron. Aluminum will naturally be oxidized from aluminum solid to aluminum 3 plus, and iron will naturally be reduced from Fe2 plus to Fe solid. So therefore, the one that is being oxidized here is aluminum solid, and the one that is being reduced is aluminum 2 plus. Okay, from this, we can determine the products of this reaction. Iron 2 plus will be reduced to iron solid, and aluminum aluminum solid is oxidized to aluminum 3 plus. Okay, but take note, this reaction is not charge balanced, so later on we'll be talking about balancing redox reactions. Okay, let's have some other examples. Let's have lithium and aluminum. Okay, in the case of lithium, lithium solid is the one that is being oxidized, and aluminum 3 plus is one that is being reduced naturally. So we have lithium and aluminum solid. Let's have some more examples. Cadmium and tin. Which one is oxidized and which one is reduced naturally? So cadmium has lower standard reduction potential, meaning this one is oxidized. Cadmium solid and tin aqueous. Cadmium solid and tin will form cadmium 2 plus and tin 2 plus. Okay, this reaction is, this equation is materially balanced and charge balanced. Okay, so that's how you make use of the standard reduction potential table in order to identify which one of the species is easily oxidized and which one of the species is easily reduced. Now let's proceed to the balancing of redox equations. Okay, so I will only teach you the half reaction method since this one is the widely used method. So for the half reaction method, we have write the half reactions for the oxidizing agent and reducing agent. Next, we have to perform a material balance, add water for lacking oxygen atoms, and add hydrogen for lacking hydrogen atoms. And finally, we have to charge balance, add electrons to balance the charges. Okay, so let's identify some of the reactions that we have done which are not materially balanced and charge balanced. Okay, say for example, aluminum and iron 2 plus. Okay, in this reaction, we have aluminum is converted to aluminum 3 plus, meaning there's an increase in oxidation number. So meaning this one is oxidation, whereas iron 2 plus is converted to iron solid or iron 0. From 2 to 0, this one is reduction, decrease in oxidation number. So first is write the half reactions for the oxidation and reduction. Oxidation is aluminum 2, aluminum 3 plus. Then we have for reduction iron 2 plus and iron. Okay, the next step is material balance. Count the number of atoms on the left and right side of the equation, and if the number of atoms match, then there's no need to worry. If they do not match in terms of number of oxygen and number of hydrogen, just add water and hydrogen ion. So in this case, the number of aluminum in the left and right side of the equation is equal, and also the number of iron atoms. So these reactions are materially balanced, but not charge balanced. In order to balance the charges, we have 0 at the left side of the equation for oxidation, and 3 for the right side of the equation for oxidation. Therefore, we need to add 3 electrons here. So plus 3 plus negative 3 is equal to 0. So this one is already charge balance. Okay. The other one is plus 2 at the left side of the equation and 0 at the right side of the equation. Therefore, we need to add 2 minus. Okay, since if we add these two equations, there will be an excess electron at the right side of the equation. We need to find the least common multiple and multiply each side by the factor of the least common multiple. So the least common multiple of 2 and 3 is 6, and 6 divided by 3 is 2. Multiply everything in the equation by 2, and 6 divided by 2 is 3, so multiply everything in the equation by 3. Therefore, for this we have 2 aluminum will form 2Al3 plus 6 electron, and at the right side for the reduction we have 3 Fe2 plus 6 electron will form 3 Fe. So mixing this or adding together these two terms or these two equations we have, we now can cancel the electrons at the products and the reactant side and just write everything as is. So at the reactant side we have 2Al plus 3Fe2 plus to form 2 aluminum 3 plus 3Fe. So this one is now the balanced redox equation. Okay, let's have some other examples. Potassium permanganate or permanganate and iron. In the standard reduction potential table, permanganate is one of the strongest oxidizing agents, and we have iron solid that can be easily oxidized to iron 2 plus. So therefore we have potassium permanganate, a permanganate that undergoes reduction, and iron solid that undergoes oxidation. Iron solid will produce iron 2 plus and permanganate will produce Mn2 plus. This one will produce Mn2 plus. Permanganate will produce Mn2 plus. So the next thing that we have to do is to write the half reactions for the oxidation and reduction. So in this case, we have Fe to Fe2 plus, meaning this one is oxidation, and therefore reduction is the permanganate to manganese 2 plus. Okay, so if you are wondering how do we calculate the oxidation number for manganese in a polyatomic ion permanganate, then I will be exemplifying that for you. So the overall charge of this species is -1. The oxidation number of oxygen is -2. So therefore, -2 times 4 is -8. And for permanganate, we don't know. So x times 1 is x. 1x. So therefore, we have x is equal to +7. So from +7 to +2, and that is reduction. Because that is decrease in oxidation number. But anyway, you can just look at the standard reduction potential to see if it is oxidation or reduction. Okay, now perform material balance. For iron, we have 2 plus, so everything is materially balanced. Perform charge balance for the oxidation reaction, so we have to add 2 electrons here. For permanganate, on the other hand, we have to perform material balance and charge balance. Okay, number of manganese is the same, manganese atoms, but the number of oxygen atoms is not the same. So we have 4 oxygen at the left side and no oxygen at the right side. So in that case, we have to add 4 water molecule. Okay, take note, add water for lacking oxygen atoms. Number of oxygen atoms is equal, but the number of hydrogen is not equal. So we have 0 hydrogen for the left and 8 hydrogen for the right. So in that case, we have to add 8 hydrogen ions here. So add hydrogen ion for lacking hydrogen atoms. Everything is materially balanced here. Manganese is 1 and 1. Oxygen is 4 and 4. Hydrogen is 8 and 8. Finally, we have to perform charge balance. So at the left side of the equation, we have -1 plus +8 is +7. This one is -1 and +8. At the right side, we have +2, +0. So we have +7 and +2. So therefore, we have to add +5 electrons here so that everything is +2. Okay, so everything is now charge balanced. Finally, balance the number of electrons that are being lost and gained. So the electrons that are being lost by iron is 2. Electrons that are gained by permanganate is 5. So take the least common multiple and multiply it by the factor. So the least common multiple is 10, and therefore we have to multiply 10 divided by 2 is 5. Multiply 5 here, and in here we have 10 divided by 5 is equal to 2, so multiply 2 in here. Okay, so account both sides. Now we have 5 Fe2 plus and 10 electrons plus. At the other side, we have 2 permanganate, 16 H plus, and 10 electrons gained. We have 5 manganese 2 plus and 8 water. So now everything is materially and charge balance. Finally, we can add these two equations. Cancel the number of electrons lost and gained, and we have 2 permanganate plus 5 iron, 5 iron ion, 2 plus, and 5 Mn2 plus, and 8 H2O. Let's have some more examples. Let's have permanganate once again. Permanganate will react with aluminum solid to form aluminum 3 plus and manganese 2 plus. Just do the same. We have oxidation is aluminum to aluminum 3 plus from 0 to 3 and therefore add 3 minus. For reduction, we have manganese permanganate to manganese 2 plus. So add water here and add H plus here. And in order to balance the left and right side of the equation, we have to add 5 electrons here. So the next thing that we have to do is to find the LCM and divide it by the factors. The LCM is 15. 5 times 3 is 15. And the factor therefore for this one is 5. The factor for here is 3. Then we have 5Al, 5Al3 plus, and 15 electrons lost. Here we have 3 permanganate, 24 H plus, and 15 electrons gained. We have 3 manganese 2 plus, and 12 water. We cancel the number of electrons lost and gained, and finally we have 5 aluminum, 3 permanganate, 24 hydrogen ion, 5 aluminum 3 plus, 3 manganese 2 plus, and 12 hydrogen, 12 water. So therefore, this one is the balanced redox reaction of permanganate and aluminum. Now, let's get to the part wherein we will apply this to redox titometry. Take note that titometry determines the amount of analyte in our sample through the volume of the titrant that reacts with that of the analyte. Redox titometry, like acid-base titometry or acid-base titration, also makes use of the concepts of solution stoichiometry. So all the calculations that you have learned in solution stoichiometry is easily applied in redox titometry. It's just that some other dynamics such as balancing redox equations are applied in redox titometry. So let's have the following example. Okay, this one is the unbalanced redox equation. The next thing that we have to do is to write the half reactions for oxidation and reduction. So the oxidation is Fe2 plus to Fe3 plus. Material and charge balance. So this one is materially balanced. Then finally add 1 electron in order to charge balance. For the reduction, we have permanganate 2 manganese plus 4 water here in order to balance the number of oxygen, and plus 8 hydrogen ion here to balance the number of hydrogens, and finally plus 5 electrons here to charge balance. Okay, find the LCM. Okay, 5. LCM is 5. Okay, therefore, we have this balance equation. 5 Fe2 plus, we form 5 Fe3 plus, and 5 electrons. Cancel the number of electrons lost and gained and add the two half reactions. Okay, so this one is the balanced equation. Finally, we can calculate the concentration of iron 2 plus, through this balanced equation. Okay, let's copy this balanced equation to the next page. Okay, it was written that 5.50 ml of 0.1 molar potassium permanganate. This one reacts with the number of with your iron 2 plus analyte. So therefore, we can calculate the number of moles of iron 2 plus from this chemical equation. But anyway, let's get to the ppm right away. ppm of Fe2 plus. We have to make use of the data given by our titrant. So we have 5.50 ml of 0.1 molar potassium permanganate, and that is the endpoint. We convert 5.50 ml to liters, and we will get 0.00550 liters. This one is 5.50 ml multiplied by 0.1 moles per liter of potassium permanganate per liter, and we will get moles of potassium permanganate. Next, we have to make use of the stoichiometric ratio that is provided by the equation. We have 1 mole of permanganate per 5 mole of iron 2 plus. And finally, we have to convert everything to milligrams, because ppm is milligrams per liter of solution. Okay. In 1 mole of iron, we have 55.85 grams of iron, and in 1 gram we have 1000 milligrams. Okay, so we have milligrams at the numerator. We cancel all the units, and we will get milligrams iron at the numerator, and divide everything by the liters of solution. Okay, how many liters? Okay, we have 0.05 liters. 0.05 liters. Finally, we will get the answer in ppm. The answer is 2,793 ppm, or 2.79 times 10 to the 3 ppm. Okay, so this is the end of our lesson for redox stoichiometry.